live. Welcome everybody to the session 2 of the Physics AS catch-up. Today, Jane Owen is going to go through particles and nuclear structure.
Okay, hello everybody, and let us start with the atom, and we'll go inside into the nucleus, and what we'll be looking at is the composition of that nucleus and what makes up protons and neutrons. We'll be looking at fundamental particles, we'll be looking at possible reactions or interactions, and types of forces that come into play at that nuclear level. Okay, so let's introduce the, am I on mute, I wonder?
No, you're fine, miss.
Okay, so the nucleus is made up of protons and neutrons. Now inside the protons and neutrons, the nucleons themselves are made up of fundamental particles, and we call those quarks. Now, the quarks that in question, there are 3 types of quarks: up, down, and strange. Now, we only need to know 2 of those. In fact, there are more, and I'll show you more a little bit later. But we also can have anti-quarks, which are anti-up, anti-down, and anti-strange. And the basically, how these quarks come together determine what type of particle they make up. So, for example, if we have 3 quarks together, that makes up what we call a baryon. And a baryon, if it is a baryon, we say that it has a baryon number of 1. Okay, whereas if we have 3 antiquarks together, then this is called an antibaryon. So we say that it has a baryon number of -1. Now, the only difference between the 2 is that the charges are opposite, the same properties, but they are opposite. Now, to make up a baryon with 3 quarks, those 3 quarks could be the same, or they could be different. So I'll give you a little example in a minute, but there are other ways in which these quarks and antiquarks can come together. If it's 3 quarks, it's a baryon. If it's 3 antiquarks, it's an anti-baryon. Sorry, an anti-baryon, because we say it's an antimatter, whereas the baryon is matter. Now, if we have 1 quark together with an antiquark, we call that a meson. And it is not a baryon, so we say that the baryon number is 0. So when we see this baryon numbers, we have to ask ourselves, is it a baryon? Then if it is, it's got a baryon number of +1. If it isn't, and it's an antibaryon, we say it's got a baryon number of -1. And if it's a meson, it's therefore not a baryon, so we say it's got a baryon number of 0. And mesons and baryons together, they make up a family of hadrons. So hadrons is like the bigger picture, if you like, and hadrons can be split off into 2, a baryon or a meson. The meson is the quark-antiquark pair, and the baryon is 3 quarks. All right. There are more flavors. So this is an example of an up, a down, strange quark. You've got an up dark arrow in a hexagon, and a down dark arrow going downwards in a hexagon, and you've got this strange kind of this symbol. And then antiquarks are kind of like the opposite, with a dark background and a light arrow going up, dark background and a light arrow going down. So the important bit here is to remember that an up quark has a charge of +2/3, okay, and a down quark has a charge of -1/3. We don't worry about strange, okay, we don't need to know much about those. We just really concentrate at this level on the up and the down. But while we're here, physicists have discovered more quarks, a charm, a bottom, and a top. And then the three antiquarks that go with that is the anti-charm, the anti-bottom, and the anti-top. They were going to call it vanilla, chocolate, and strawberry, but they decided on charm, bottom, and top. Again, we don't need to know this at this stage, but it's interesting because it tells us actually how many quarks are there in total. There are 6 quarks in total, and the 6 antiquark pairs to go with that. So let's have a look at constitution and examples of a baryon. So we've got 2 baryons here. We've got a proton, and a proton, has got an up, it's got a down. I mustn't put a line underneath or on top because that will give you the idea that it's antimatter and it's not. It's got an up, a quark, it's got an up quark and a down quark, so an up, up, down. So if you're answering any questions on the makeup, the quark makeup of a baryon, you must kind of like include in these the actual individual charges. So an up is plus 2/3, an up is plus 2/3, add those up together, 4/3, take away minus 1/3 for a down quark, because a down quark has got minus 1/3 charge, and then you get in total a charge of +1, okay? A proton has got a baryon number of +1 because it is a baryon, okay? And we don't need to worry about the strange. It's not made up of any strange particles, so it's not a strange. Okay, so that's an example of a proton. Now, an antiproton would be exactly the same, but it would be an anti-up, an anti-up, and an anti-down. So it would have a charge of minus 2/3, minus 2/3, plus 1/3, which means that the total charge would be -1. So it's the same makeup, but the anti-quark, the same quarks but anti-quark, and therefore it's the opposite charge. So it's the same properties but the opposite charge. And because it's an anti-proton, then we can say that it is an anti-baryon, so we say that the baryon number is -1. Okay, now looking at an example of a meson, you've got here a up and an anti-down. Oh, hold on, no. What have we got here? We have got meson. We've got an up, anti-down. So let's have a look at that. An up has got a charge of plus 2/3. A down quark is minus 1/3, but an anti-down quark would be plus 1/3. So therefore, 2/3 plus 1/3 equals a charge of +1. And that ties in with a pi plus particle, which is a meson, which we say either pi plus or a pion plus. Okay, and that's an example of a quark-antiquark pairing. And that's how you would look at it. You'd break it up into the individual quark-antiquarks and put the charges together to see if you can match it with the charge that the quark has got. Okay, so we've got here a whole range of particles. We know that neutrons and protons are baryons, okay? We know that pi plus, pi 0, pi minus, they are mesons. And we've got a whole other load of particles here that you don't necessarily have to know about, but it's kind of interesting because you can see that they're different sizes, and those sizes represent different rest energies. So they've got different energies involved with them. So for example, we've got deltas for baryons, we've got lambda, we've got neutrons and protons, which you should know about and try and remember, and you've got sigmas. Now, you don't have to know any of these, but it's interesting. You can see and have a look at the quark makeup. Notice with baryons, they've always got 3 quark combination, whereas with mesons, there's always 1 quark and 1 antiquark pairing. Okay, so it just goes to show the scale and the number of baryons and mesons out there, even though you only need to know the neutron and proton and probably the pi family. But you could be asked anything about any of the others and what you think the makeup would be. Okay, right, so let's take it a little bit further and have a look at the baryon makeup. Now, it's got 3 quarks in it, and these 3 quarks are held together by what we call the strong force. I think perhaps what I ought to do is just go back just to do a little bit of a vision on this nucleus structure. You've got the atom, you've got the nucleus in the center. You know that the nucleus is a positive charge, and there's a little electron flying around that positive charge. And there is an electrostatic attraction between the negative electron and the positive nucleus, and this is the electromagnetic force. Inside those nucleons, though, are the 3 quarks. And you might say to yourself, well, how on earth inside the nucleus, where you've got lots of positive charge, so you've got protons, you've got neutrons, and those protons will want to repel one another because they're all the same charge and they want to get away from one another. So they must be a force that overcomes this electromagnetic repulsion in order to kind of like bring them together so that they sit comfortably in the nucleus with one another around. And that is the strong force. So the strong force is responsible for the nucleons staying within the nucleus. And then if we have a look, so if you push those nucleons too close together, it will want to kind of like repel to an equilibrium position. Equally, if you try and pull them apart, they'll want to come back to an equilibrium position. So there is kind of like positioning, ideal positioning within the nucleus. There's a happy medium. Now, if we have a look inside the actual baryon or proton or neutron makeup, you've got these 3 quarks held together by the strong force. If you supply enough energy, for example, bombarding it with another particle which has got a lot of kinetic energy, then this strong force here can get stretched and the quark will get kind of like try and come away, but it can never exist on its own. It can only go back to its 3 quark kind of baryon status. And what happens is all of that kinetic energy that goes in to stretch those bonds can turn into and create another particle which is called a meson. And that is why mesons can appear in a reaction or equally disappear. Because what you've got in terms of a meson is a quark-antiquark pairing, and they probably won't exist for very long before they want to annihilate one another, because say one has got a charge of say 1 positive, the other one will have a negative charge, and they will want to annihilate one another and produce photons of energy. So instead of existing as a particle, it probably will want to annihilate itself and turn into photons of energy. But you can see that the strong force has been responsible for creating the meson in the first place. So if we see a meson in an equation, then we know that perhaps possibly that the strong force has been influenced the baryon in forming the meson. It depends how much kinetic energy is involved in the reaction, because what could happen is you could have a baryon colliding with another baryon, and there won't be enough energy to stretch that strong force in order to create this other particle. So what could happen is that they could just collide together and repel one another because they're the same charge, and go off in different directions. And then it's just electromagnetic force that's involved. But when it creates a meson, then you know it's the strong force that's involved because it's created that. All right. Okay, but there is another fundamental particle, and that fundamental particle is a lepton. And an example of a lepton is an electron. Now, there aren't just one lepton. There's also a pair to go with that called an electron neutrino. And an electron neutrino is a very small charged particle. It's got a very small neutral particle. It's got no charge. Okay, very little mass indeed, and zero charge. And contrary to this, there is also the anti-lepton and the anti-lepton, which is an anti-electron, and an anti-electron neutrino. And you might say, well, what charge is it going to be if it's a neutral charge? But you can have, so an opposite charge to an electron would be a positron. That would be the anti-lepton. So therefore, that has got a lepton number of -1. So the charge would be +1, but the lepton number would be -1 because it's an anti-lepton. In addition to this, you can get an anti-electron neutrino. So the charge is still 0. So we write it like this with a hat on to show that it's an antimatter. And the charge would still be 0. Charge 0. And the lepton number would be -1. Okay, now that's not the whole story, because you can also get tauons and muons, which are leptons. So it's not just electrons that are leptons, there are also tau minus and mu minus, and you can also get the corresponding electron neutrino, tauon neutrino, and muon neutrino. And also you can get the anti-leptons of the positron and the anti-electron neutrino, the tau plus, the mu plus, and the anti-tau neutrino and the anti-mu neutrino. Okay, so again, there are 6 different types of leptons and 6 different anti-leptons, but really the only ones that you need to worry about are an electron and an electron neutrino, because if you find one, you're most likely to find the other one, but it could be the anti-electron neutrino. So there's a summary table, and that summary table will be in any data booklet that you've got, and it's also in the syllabus. Now the syllabus, if you're doing WJC, is at the end of this class notebook, should you want to refer to it. So let's have a few examples here. So I have one here, helium goes to lithium, plus an electron plus an anti-electron neutrino. Could it possibly exist, you ask? So we have to look in terms of baryon number, lepton number, charge number. All 3 of those will be conserved. So just to clarify, if something has got a lepton number of +1, it means that particle is a lepton. For example, an electron is a lepton, so has a lepton number of +1. If it's an antilepton, it'll be -1. So we've got, in a helium, we've got 2 protons, and we've got 2 protons and 4 neutrons. In this lithium here, we've got 3 protons, and we've got therefore 3 protons plus 3 neutrons. So this means that one of the neutrons in the helium has turned into one of the protons. So a neutron has turned into a proton plus an electron plus an anti-electron neutrino. Now let's have a look at it in terms of charge. Neutrons have got no charge, 0. Protons have got a charge of +1. Electrons have a charge of -1. And anti-electron neutrino, tiny little neutral one, has got no charge. So charge here is conserved because 0 goes to +1, -1, 0. So that is conserved. So if charge is conserved, this reaction can go ahead. But we have to look now at the baryon number. The baryon number for a neutron, it is a baryon. So we say it's got a baryon number of +1. Proton is a baryon, so it has a baryon number +1. The electron is not a baryon because it's a lepton, so that has got no baryon number. And an anti-electron neutrino is not a baryon because it's an anti-lepton, so it's 0. So therefore, again, we've got conservation of baryon number, so we say it's conserved. Again, reaction could go ahead, but still, that doesn't give us the whole picture. We've now got to look at the lepton number. Neutrons are not leptons, so 0. Protons are not leptons, so 0. Electrons are a lepton, so that is +1. Plus, an anti-electron neutrino is an anti-lepton, so that's got a lepton number of -1. So we're going 0 to 0. Now it's not good enough for you just to kind of like sidetrack all of that and just go 0 to 0. You've got to show the process. And you might say, well, that's mundane, I can see that straight away. But you've got to show to the examiners all of the steps in between of how you're getting to where you're going, okay? So that is conserved. So this reaction could take place. And in fact, what we can see over here on the diagram is just this reaction. So what has happened is, I'm thinking, which way around is it? So we're seeing, let me have a look. I can't remember which way round it is. We've got a particle there. We've got the decay of the lithium. So this is the lithium here. So that is the lithium. And this here is the beta particle. This is the electron, also described as a beta particle. And a beta particle emission, we call it a beta emission, because it could be an E-, i.e. an electron, or it could be an E+, i.e. a positive beta emission. Okay, so something must have, something must have been ejected upwards in this direction maybe, but we can't see it in this bubble chamber because bubble chambers work when it's a charged particle and you've got saturated alcohol around the charged particle as it passes through. So something's happened at this point, and this was the helium particle, and the lithium goes in this direction, the beta goes in this direction. Both of those are being charged particles, but in another direction will have to be the anti-electron neutrino. And of course, because it's neutral, it doesn't appear, because the saturated alcohol will only make kind of tracks around charged particles, much like a plane flying overhead, and the water condenses to make those trails when the aeroplane's passing over through the atmosphere. Okay, all right, moving on. Okay, I think I'm going to, shall I do that one? Yes, so in summary, when you're looking at reactions, you've got to look at whether there's conservation of charge, whether there's conservation of baryons, whether there's conservation of leptons for it to happen. I'm just wondering if I ought to go on. If I've got time, I'll come back to this reaction to identify the particle X. And we do exactly the same as if we did above in terms of Q, B, and L. I think what I'm going to do is I'm going to just carry on, so that then at least I've completed the whole topic, and then if I've got time, I'll come back. Now, we look sometimes at in a more fundamental level. So if we look at what's going on here, we've got a neutron going to a proton. So I might just put it over here, actually, while I've got it all here. So a neutron goes to a proton plus an electron plus an anti-electron neutrino. Okay, right now, a neutron will be an up, down, down. A proton is an up, up, down. So we could look at it on a fundamental level in terms of what's happening at the quark level. Plus an electron plus an anti-electron neutrino. Now we know that works, and we know that's possible. Now have a look in terms of what's going on with quarks. I'm going to cancel those out, I'm going to cancel those out, because it's the same on both sides. But look, this down changes into an up. We say that there is a flavor change, and that quark flavor change is responsible by what we call a weak interaction. Now, we don't tend to say weak force, we tend to say weak interaction. And this, when we've got a reaction like this, and we have a quark flavor, we can say that what's responsible is the weak interaction. And another clue here is this presence of any neutrinos. So if you see any neutrinos in the equation, then you know that probably the weak interaction is responsible. Whereas if you see in any equation, for example, this pi, so if I give you an example of a pi, say if we have a proton plus a proton goes to produce a proton and a proton plus a pi 0. Okay, now could that happen? Well, the charge is conserved, 2, 2. Baryon, okay, so baryons conserved because you've got 2 baryons on this side, you've got 2 baryons on this side. Meson is not a baryon, so that's got a baryon number 0. And there are no leptons involved here. So what's happened is that these protons here that are colliding together have a very, very high amount of kinetic energy, enough to form this meson. So if you see this meson present, then you know that it's the strong force that is responsible for producing that meson, because these protons, these charged particles, have very, very high kinetic energies. So that it's the kinetic energy that goes into the system to stretch those strong force that produces this meson in the end. If I had a proton and a proton colliding together but didn't have enough energy, kinetic energy, and it just produced rebounding protons and it didn't produce a meson, then the only force there responsible is the electromagnetic force. Because what you've got there is you've got colliding particles that are the same charge, and so therefore you want repulsion, and it just bounces off one another. So we say that electrostatic repulsion, we say, is responsible by the electromagnetic force. Whereas if a meson is produced, then it's the strong force that is influencing that reaction. There's one other I want to look at in terms of forces and reactions and what's going on, and that is this could happen. So if you've got a pi zero, it could be an up anti-up, or it could be a down anti-down. We don't know which one it could be either or. Okay, so we've got up anti-up. Now, up has got a charge of plus 2/3, anti-up has got a charge of minus 2/3. So what happens is that will annihilate one another because of that attraction of those charges coming together, and that will turn into 2 photons of energy. So you can relate E equals mc squared, because the rest mass of the meson would be equal to the energy of the photons produced. And it would have to be 2 photons because the 2 charged particles will be moving in one direction, and therefore for conservation of momentum you would have 2 gamma photons produced in opposite directions. Okay, and that would be the electromagnetic force which would be responsible for this. So even though we've got a meson up here, in this case it would be the strong force because it's been created from those baryons and giving them enough energy to do so, whereas here this meson annihilates itself to form 2 gamma photons, and that is as a result of the opposite charges attracting one another, and that is responsible by the electromagnetic force. Okay, now I think, unless I've got any questions, can I ask if there are any questions? Otherwise, I will go and look at that reaction.
No, nothing that you need to go over. Thank you, Jane.
Okay, all right, that's fine. So what I'll do is in the last 5 minutes, we will have a look at this one and see if we can identify what particle X is. Okay, so we've got chlorine going into argon, and we've got an electron neutrino here, and we wonder what X is going to be. So let's have a look at it. We've got 17 protons here. We've got 18 protons here. That means, and if we've got the same number of protons and neutrons all together, that means one neutron has turned into 1 proton. So that's what's going on here. Okay, so we can write it as neutron plus electron neutrino goes to a proton plus particle X. Now let's give it a question mark. Okay, and let's look at it in terms of charge. So in terms of charge here, what's going on? We know a proton is positive, and we know electron neutrino is neutral. So in terms of charge, neutron has got no charge, 0. Electron, a neutrino has got no charge, 0. But a proton has got +1, and therefore this X here must have, therefore X charge equals -1 to have conservation of charge so that it could take place. So then we would get 0 to 0. So it must have a charge of -1. Then let's look on the baryon front. Neutron is a baryon, electron neutrino is not a baryon, proton is a baryon, therefore X, okay, is not a baryon. So the baryon, because we've got to have conservation of baryon, that one will go to 1. So therefore, X cannot possibly have can't be a baryon. And finally, lepton. Okay, you've got no neutrons, not a lepton. Electron neutrino is a lepton. A proton is not a lepton. So therefore, X must be a lepton. So therefore, the particle's not a baryon, it's a lepton, and it's got a charge of -1. Therefore, X could be an electron. All right. And just before I finish, this is really interesting, this little diagram. This is showing all of those different swirls in different ways. Those are paths of charged particles as they pass through the alcohol in a cloud chamber. And what you have is you have a magnetic field above and below, so that the charges will move in different circles, in different directions. So one charge will go one way and another charge will go in another direction. Now, the fact that it spirals downwards means that that charged particle is running out of kinetic energy and it's getting slower and slower. And so therefore the circles and the spirals get tighter and tighter. But it's this point here which is interesting, because it looks like this. All right, the path looks like that. And what's happened is a neutron is traveling along here, and then it undergoes decay, and it probably undergoes that beta decay that we had before. So you've got a neutron going along, and then the neutron goes into a proton plus an electron plus an anti-electron neutrino. Now this one and this one will not appear because they haven't got a charge, so it won't form a trail. So you've got one which is kind of like at a low angle, and you've got another one at a higher angle. Now it all depends on the speed of the proton and the electron. And I would have thought that this one would be the electron and this one would be the proton, only because the electron's going so fast and much faster than the proton because it's much lighter. But it's also got something to do with its mass. The fact that it is light means that it can be bent more easily. So it just depends on the ratios of the speeds compared to the ratio of the masses. So I could be wrong there, but you've got the idea that this neutron, something happens at this stage where it breaks up and goes into this V-shaped area. Okay, all right, I think, so to review, we've looked at the structure of the nucleus, we've looked at the structure within the nucleus, the particles inside the nucleus made up of quarks. Quarks are a fundamental particle as well as a lepton, and it's how those quarks and antiquarks combine with themselves to produce baryons and mesons. And then we looked at baryon conservation, lepton conservation, and charge conservation in order for a reaction to take place. And I have given you tables below of more, kind of like the particles involved. And then right at the end here is a summary on the 4 different types of forces, and gravitational not having an effect because the masses are so small. And these are all the different types of baryons and mesons and the quark makeup and the rest energies. And like a proton is stable, a neutron is only stable in a nucleus, but the rest really don't exist and stick around for very long. Okay, and then finally, that's the whole of the subject content for WJEC and what I've tried to cover. And I hope I've covered it all, but with a little bit more for you to see how it fits in.